can start. So Tuesday we were talking about how we can train a neural network in general like a convolutional neural network, and then we talked about how we need like a loss function and then an optimization algorithm where we used gradient descent, and then we were talking about stochastic gradient descent. So the idea was usually when you train your networks on a data set, on a training set, the data set is very huge, and if you can't actually fit all of that data into your memory at once, and therefore gradient descent is usually not possible. Therefore what we do is we perform stochastic gradient descent, which is called SGD. That's an optimization process to train your network. And what will happen is if you do that, you have to select like a few data points at once, and this gradient descent will not be like when you update the weights, when you back propagate computing the gradients. So it will not be like based on all the data points, right? So it will be only based on the samples you have at that moment of time. So when you randomly pick samples, again, you don't just like pick one sample and train your network, because then what's going to happen is whatever loss you get using that sample, that loss will be very specific to that particular sample, and you cannot generalize that loss to the whole data set. Right? So then when you update the training, the model parameters, that update will be very specific to that particular sample. So that's not a good idea. Therefore, what we do is we take like a bunch of samples, which we called a mini batch. And this is called like batch size in your training. And once you have that batch, you then can compute the loss function, because then that loss function is not like based on one sample. It's like an average loss based on all the samples in that particular batch. And initially you start with like a random weights of all the kernels, whatever kernels or whatever parameters you have in your network. So they could be like kernels if it's convolutional, they could be just like weights for your neural network layers. And then you need a learning rate, which will be used to take those gradient steps to do the update. Right, and this was like the whole training process. I think we talked about this as well. So what you do is you randomly shuffle like your training set. Let's say you have 100,000 images. You will randomly shuffle that, and then you start from the first sample. And then let's say your batch size is 100. You start picking 100 samples. Then you do the forward pass, compute the loss, then compute the gradients, do the backward pass, update the network weights. All right. So that's like a one step. And that's also called one iteration. So that's another important term you should know. So going through one mini batch forward and backward is called one iteration. And then you just repeat that iteration, the steps of that iteration like throughout your training set. So you will then select like next 100 samples, repeat the same process. And when you're done with all the samples in your training set, that's called one epoch. And the significance is like your network has seen every sample in your training set at least once. All right. And once one epoch is done, then you again shuffle your training set and repeat the whole process again. All right. So then what will happen is initially, since the network weights were randomly initialized, then the loss function which you will get, it will be pretty high because those were random weights. So whatever prediction your network will make, it will not match the ground truth. It will be far away from that, right? So we are starting. So the x-axis here is showing number of iterations, and the y-axis is giving you the loss value. All right. So 0 is like the initial point when you initialize the parameters, and you can see like you have a very high loss. And as you keep training, keep moving forward, your loss is going down. So one thing you can observe is that your loss is not always going down. It's sometimes rising as well. And the reason is it's trying to find like a local minima because it is trained on mini patches, right? It's never seeing like the whole training set at once. So sometimes it may happen that the batch you have selected, it's leading your network to a direction which is not like towards the global optima. But eventually like it will try to converge and move towards like a better solution. So it keeps decreasing. Okay. Now, if you try to visualize this, what actually is happening is, so if you remember, like we have a loss function, right? So that's a function, and if it's a function, then you can try to visualize it. And let's say it's a two-dimensional function, and of course, whatever you visualize in two-dimensional, you can generalize it to n-dimensional space. But of course, you can't. It's not easy to actually visualize n-dimensional space. So that's what we will do here. That's what we'll do here. So this is a two-dimensional, let's say, loss function, and the center over here is like the minima. All right, so this is kind of a dip, and these are like high loss values. So when you randomly initialize your network weights, let's say that's x0, then ideally what you want is you want to move towards this direction and reach this point, right? So now what's going to happen is when you train using gradient descent, you will have some learning rate, and then you will get some gradient value. So depending upon what's the gradient value and what's the learning rate, you will take these tiny steps, and these steps should ideally go towards this minima, which is like the solution which you are looking for. But usually when you train in real world, you won't go directly from like this point to this point in a straight line. So you will have some oscillations. So you might not go in the right direction, but eventually, like if you follow like the actual path, it will be towards the global minimum, and that's exactly what's happening here. So sometimes your loss is increasing, sometimes it's going down, but overall, if you look, it's converging, it's going down. Okay. Question from Russia: which algorithm does the loss function use to calculate the local minimum? So we don't know what the local minima is. We even don't know what a global minima is. We just assume that the loss function will have some kind of surface, and there should be some local. I mean, we don't want local minimas. That's not like desirable. We assume that we'll have a global minima, and then when you optimize, it will go towards that direction. So probably I didn't get your question. So right now we are using gradient descent, right, for the optimization. So Ruchia, can you explain like what's the confusion, or what, maybe try to rephrase?
Hello, Professor. No, actually, my question, I mean, you already answered my question. So I just wanted to understand how does it calculate the local minima or the global minima point?
Okay, yeah, so it's not computing local and global minima, it's just computing the loss value,
Okay.
and that value will like in somewhere in that surface, right? So it could be local minima, global minima, but whatever it is, we always go towards like the gradient direction, right?
Yeah, I got it.
Okay, all right. So question from Amelia: can you elaborate on what you mean by loss decreases? Because on the graph, the lower number is 10, not 0. Yeah, you can actually ignore the labels. So that's fine, just ignore it. So just assume that this is like higher loss and this is a low loss. Okay. Question from Sayed: why the loss are negative and the absolute value is increasing? Yeah, probably just ignore it, because it will depend upon what is the loss function, right? So sometimes you might to minimize it, which could mean that you want to go from a higher value to close to 0, right? But sometimes it may happen that your loss can also have negative values. So in that case, if it's going towards a negative direction, so that could be a gain. So that's exactly what's happening here. But probably you can just ignore it at this point of time, right? All right. So that's how it works. And usually what happens is like depending upon like what's your step size, right? The step you're taking. So that will depend upon the learning rate. And if you remember the equation we have, like for gradient update, we had a coefficient which will determine like how big your step should be. So that parameter, that's a hyperparameter, very important hyperparameter when you train your network. That's called learning rate. So that will determine like how big these steps will be. So if you use a very high learning rate, then you will see like these steps are going to be very large, right? You will quickly reach this point, and that's what we want. But what may happen is if you take bigger steps, you may actually miss this point as well. So let's say if your learning rate is too high, then that may cause like a jump from this point to this point, right? And then you are totally missing your minima, and therefore that hyperparameter is very, very important. So question from Steven, can you just restate how you measure loss each epoch to identify going up or down, specifically a measure of test accuracy in output layer? Okay, so that's a good question. So if you remember, like last lecture, we talked about we need a loss function which can estimate how good your network is performing. So what that function or what that loss function will do is it will have access to ground truth, what exactly the output should be, and then we will also provide the function the values or the predictions which the network is giving, and then that function can actually compare those two and some mathematical formulation, and then give you a value, a loss value, which will say that whether we are close to the ground truth or how far away we are from the ground truth. So then that's the quantification we are going to use, and that's not on the test data, that's still on the training data, and then we use that loss value to actually update our weights. So did that answer your question, Stephen? So that loss is not computed each epoch, it's computed each iteration for the mini batch. So we compute it for each sample, and then we average it for all the samples in the mini batch, and then use that loss function to actually do back propagation. Is it clear, Stephen? Okay, when you say a measure of how far away, roughly how is that represented? All right, so let me actually go back. Just give me. Oh, that was previous lecture. So that I will have to. Oh, okay, we have it here. Right. So now this you understand, right? This is the ground truth. So let's say we are talking about classification. So classification will say like whether a particular object category is present in the image or not. All right. So this is the ground truth, and this is the input, the actual image. The W is the network parameters. So passing these two things together to the network, so F is your network, will make some prediction whether that object is present or not. All right. So then let's say Apple was present in the image. So the ground truth should say 1 for Apple. And depending upon what your network is predicting, let's say it predicted 1, right? 1 means Apple is present. Then you can easily compute a value using these two terms, right? It could be just like, let's say, difference between these two values. So that's called L1, uh, L1 difference, right? So then you can just subtract these two. And if it's 0, you say, okay, loss is 0. And if your network is saying 0, then again you subtract, it will say 1, which means like you have a higher loss value. And again, I think in the last lecture, we talked about a few loss functions as well, which you can use to compare the ground truth with the network prediction to quantize like how good your network is doing. So I hope that was a question, and if not, please let me know. Yeah, we talked about cross entropy as well, right? We talked about mean square error. So all these are different forms of like seeing that how good your network is performing. Somehow I missed that when I went back. All right, so yeah, I think it should be clear. All right, great. That helps some. Okay, but that's like, I think that's very basic. It should uh, it should be very clear. So I'm not sure which part was not clear. So if you can maybe rephrase, you can use your mic if you want, because I want you to understand it very clearly.
So, I guess where I'm having trouble picturing is
I can barely
you're
hear you,
looking.
Stephen.
I'm sorry, I'm losing my voice this week. So the question I guess I have is are we just doing? We're plugging into whatever our loss function is, whether it's right or wrong, or one of the other varying loss functions that we're using to estimate it. I guess the question is how do we measure anything that's just right or wrong per image on a different scale besides just it matches or doesn't match. You said that there's a measure of accuracy. We're just looking at the whole batch at that level to say we've got 90% of these are accurate and this one's off on 10 out of these images, so keep adjusting. Or I guess the partial or level of accuracy is where I'm not 100%.
Okay, so I could barely hear you, but I think whatever I got, I will rephrase it. So you are saying that you can plug in like any loss function, but you want to understand what it actually represents, right? And how exactly it's measuring how good the network is doing. What is that your question?
Pretty much.
Okay, so first of all, as we discussed last time, whatever loss function you use, it should be differentiable, because you need to compute gradients, and those gradients will flow back into your network to actually update your weights. So if a loss function can't be differentiated, then you cannot use it. And that's the reason you can't use like the actual measurements such as accuracy or precision, all those things, right? Because those will not be differentiable. And so for example, MSE loss, right? So that's kind of, you can say, a good approximation to accuracy, not exactly the same thing, because you can. Okay, so let me put it this way. So let's first talk about just binary classification. And binary classification is, let's say we have a problem where we just want to say, given an image, whether a face is present or a face is not present, right? Now, in the ground truth, what we will have is, for each image, we will know whether a face is present or not. And usually what we do is we use one-hot vector representation. And if face is not present, we will use a number 0 for that. And if a face is present, we will use a number 1 for that. Okay, so that should be clear. And so if that's a ground truth, we expect our network to also predict those values. So what that means is, if an image of face is given, the network should say 1. If the image of non-face is given, the network should say 0. And of course, the network will not do that perfectly. So it might give you some values between 0 and 1. So it could be very small value, maybe 0.05. It could be very high value, 0.95, or somewhere in between. So, so let me ask you this. So if your network is saying it's 0.05, it means that it's trying to say face is not present, right? Because 0.05 is very close to 0 as compared to 1. So then we can use that difference between 0 and 0.05 to actually quantize how good your network is doing. Similarly, if your network says it's 0.95 or maybe some high value 0.80, then again we can quantize, okay, the network is doing good because zero point 0.8 is close to 1, but we can say that it's not as good as if the network would have predicted 0.95. So does it clarify your doubt?
Yes, that helps. So we have a target value or set of values
Mm-hmm.
that we get beyond the binary case, and our functions are meant to, our results are meant to estimate and be classified as one of those different values, whatever the target is. And yes, I think that definitely makes it a lot clearer. I appreciate it.
Okay, all right, good. So let me elaborate on that. So That's binary classification, and you can easily generalize that. Now, let's say if you have a problem where you are synthesizing the whole image, right? It's not classification anymore. So even in that case, if you are synthesizing one image, then you will have a ground truth, right? Which image you want to synthesize. Then what you can do is you can actually compare pixel wise. For each pixel, you can compute the difference and then average that difference over all the pixels and all the channels if it's a colored image. And that could be your loss value, right? So it's always about how close you are to the ground truth. And again, that ground truth could be anything. It could be video, it could be image, it could be just a number. Okay. All right. So I think let's continue. So that was gradient descent. And so sometimes what happens is your so as I said, like your optimization algorithm might oscillate. It might not follow the actual path. So then sometimes it's useful to actually use momentum. And what momentum does is it will look at the direction of your optimization in the previous step, and then try to like follow that direction. All right. So in this case, it's just fluctuating like this. But if you make use of like so let's say we are at this step, right? So then it will look into like the previous direction. So it was going in this direction. So it will not take like a U-turn. It will keep this in mind and maybe keep moving in this direction, but slightly towards this. So it will be like a smooth curve instead of a zigzag. And that's called momentum. And there are a lot of variations of this. I will just briefly cover like the intuition why this is useful. So the normal update rule, you all know that, let's say you have a weight parameter, let's say theta t, then this is your learning rate, gamma, and then you compute the gradient, and L is your loss function. So you compute the gradient with respect to this parameter theta, and then based on this learning rate, which decides like how big your step will be, you make this update, and that will give you the new weight for that particular parameter. And this is only taking into account the gradient at this point of time. But in momentum, as I said, we also consider like the gradient or the direction where we were going in the previous step. So what we do is we also take that into account, just add this. So this is the gradient, you can see t minus 1, right? The previous step. And then again, we have one more hyperparameter. You can control like how much of that we want to use. And then the direction where it's going, it will be kind of smooth instead of a zigzag motion. Okay, so what happens is then when it's try to converge, it will be like fewer steps. The other thing is, as I said, the learning rate, right? Let me see if there are any questions. In slide 28, can we say that is the learning part? So question from Mud, can we say that is the learning part? Right, exactly. So this is the learning, actual learning, because as we are moving closer to, so let me go to slide 28. So this is the actual learning, right? You compute the gradients, and based on the learning rate, you update the network parameters. And this is not just one parameter. You're actually updating all the parameters of your network. So for each parameter, you are computing this partial derivative with respect to your your actual loss. So this is the actual learning. So that's correct. So yeah, that's clear to me. The question from Ahmed: in practice, how many previous steps is mostly used for momentum? So yeah, this variation I showed, like it's just single step. And I mean, there are variations where you can use like multiple previous steps. So there is no like ground rule how much you should use. Okay. And again, I mean, this is like a evolving research area. So there are a lot of variations just even in momentum itself. So don't worry about like how many steps are required, but if you understand the general idea what's happening, so that's more useful. But yeah, I think that was a good question. Okay, so
Professor,
Yes.
I had a query regarding the mini-batch training. So why is that we backpropagate after every mini-batch and not after completing the whole epoch?
After the whole epoch, and I think that's a very good question. And
Like
again,
by
that's
doing that, we
something.
can reduce the number of backpropagations.
Yes, you can. And the issue is, like, first of all, how will you, so you'll have to keep accumulating the gradients, right? So that's something
Yes.
like, you load all your data into memory
Yeah.
and then just take one step, right?
Yes.
So the solution you're offering is you can just keep storing those gradients or loss values and then
Yes.
update at the end.
Mhm.
So one reason is the way we train these are large data sets, right? It has been shown that if we use fewer samples,
Mhm.
that is actually much better as comparison to like the using the full data set,
Okay.
right? And the reason is when you take a full when you use the full data set, so that mean in a way when you can say that, okay, that's more confident, right? But
Yes.
again, the if you think about the loss function, the curve, it's not a convex curve. It will have lot of minimas, right?
Yeah.
So when you use like the full set, we don't know where it will go.
Yeah.
So usually when you do like small mini batch, you are adding some kind of stochastic behavior there, right? So that
Okay.
usually helps, and that's one
Okay.
thing. But usually what we do is, if you want to increase your batch size and it's not fitting into your memory, then what you do is you keep accumulating like these gradients. So you compute gradients for each mini batch, you can
Okay.
store in memory, and then you decide like, okay, what's the batch size, effective batch size, and you keep accumulating those gradients. And then once you have reached that number, then you do like one time upgrade. So that is something which
Okay.
is okay.
Okay.
So but
Thank you,
that was a good
Professor.
question. That was a good question. Now I would like to add one more thing there.
Okay.
It's updating weights, that's not computationally expensive,
Okay.
right? So if you look at this equation, it's just a subtraction, right? It's just like increment or
Mhm.
decrement to your actual weight value.
Yeah.
And this is not computationally expensive. The expensive part is computing or this derivative, this partial derivative,
Derivative.
and that
But
you
what I
have to like
thought is,
back propagate.
Professor, is that like we are like calculating the weights, like we are updating the weights for each and every layer in the network. So I
Mhm.
thought since we're doing that for all the layers, maybe it might be a computational expensive process.
Yeah, computing gradients is expensive. That's what I'm saying. But updating weights, it's not.
Oh, okay, okay, yeah, okay. Another query, Professor.
Mhm.
It's regarding the mini batch itself. Why is that we usually prefer mini batches in terms of power of two? Like usually it's 4, 8, 32, 64, something like that.
So I think to be fair, like if you think about how your memory in computers is built, it's a binary
Okay.
system, right?
Yeah.
And the way the memory is mapped, it's always power of two, right?
Okay.
So using those numbers mean it's more efficient.
Okay.
That's the only reason. But it doesn't mean that you can't use like any odd values. But that will be like inefficient. Sometimes it may not matter. Sometimes it may. It's just that
Okay.
if you need like a memory chunk from your RAM or from a GPU, if it's in power of two, it will be easy for the computer to allocate that memory, right?
Yeah.
As compared to if you use, let's say, 33 or 34, then and
Mhm.
you will end up like in some kind of fragmentation in your memory.
Yeah. Yeah.
But of
Got it,
course, I
Professor.
mean, we have optimizations in the operating system as well. But again, if you code efficiently, then you don't have to go in that direction. So that's the only
Okay.
reason. All right.
Okay. Thanks a lot,
I think,
Professor.
all right, a question from Connor. Will small batch sizes always lead to memorization of training set? That's not true. it's not memorization. I mean, to some level you can, because if you have a lot of parameters, right? And if you just pass maybe a few samples, then your network will be able to actually memorize what it needs to have to actually make the right prediction. And I mean, you can say that, okay, that memorization is causing like a bad conversion, causing the bad convergence of the network. But at the end, I mean, you again, in the next batch, you will show some different samples, right? So then it will go in different directions. So eventually, I mean, it will not be memorization, because whatever you are memorizing, then you are forgetting it very soon. And that's the reason, like when you train on very small batches on a complex data set, you will not like get very good training. But I think that is a very good comment, like small batches can lead to memorization, but not like overall, just in that iteration. So I hope that was clear. Okay, all right, good. Okay, so that was momentum. And then as again, I said like learning rate, it's very important to have a parameter, and it will determine like how fast you will converge or whether you will be able to converge or not. So even if you look at this example, if you use a very small learning rate, then it's going to take very small steps. It might go in this direction, but again, it will take a lot of time. All right, so now again, these things are complicated. Once you like get used to like the training of networks, then you will be more familiar. Now let me give you some insights like which will be useful when you train your network. Now what's going to happen is, when you train your network, you will monitor the loss value, right? So this is x-axis is like your iteration or your epoch, and again y-axis is the loss value. So starting point, you will get a very high loss, and if you plot it like with each iteration or each epoch, you will observe that your loss ideally should go down, and you might get like different curves. And to be fair, I think in your training you will never get like these perfect curves. The curve I showed you earlier, where there was a like lot of fluctuation, that's more reality. But this is, I think, better for understanding. So let's start with the yellow one. If you use a very high learning rate, then what will happen is it will try to converge, but then your loss will actually uh, try to increase. It will keep going up. Okay. Now, if you try to understand what's happening there is, let's say A1 is your initial point, and you use a very high learning rate, which is causing you to take big jumps. Right. So then what will happen is you might go from this point to this point, because this is the gradient direction. But the next step you will take, because of a high learning rate, you might just jump across like the minimum point, and then you will keep going away from this minimum. So that's why the loss is actually increasing, right? So high learning rate is very high learning rate. Learning rate is not good, but this is like a sign when you try to monitor your loss. Then you need to lower your loss, lower your learning rate. Now let's go to the blue one. So blue one, you can see that your loss is actually constantly going down, but the rate at which it's going down, it's not changing. It's kind of a straight line. Again, which means that it's a very low learning rate. It's moving very slow. So if you increase it a bit, you might get a better curve or a better learning. And then you will try to decrease it. Let's say you get to the red one, then you can see that it's actually going down and then kind of saturating. And that's kind of a perfect learning curve. We call this like maybe L-shaped curve. So that's a good learning rate. So the other curve you will observe is like this, a green one. It's going down pretty quickly and then it's saturating. So again, this is due to like a high learning rate. It means that it's maybe stuck at some local minima or somewhere, right? So very quickly it go to that local minima and then it's not changing at all. So these are just sample curves which you might observe. And as I said, this is like, these are synthetic curves. In reality, you will have something entirely different, very a lot of fluctuations. But if you look at the general trend, you will see these patterns. Now, yes, Sarath, you are saying something?
Sir, I mean to ask, does this loss converge at any point on the x-axis to same point as the last curve?
In the x-axis, yeah, this red curve is converging, right? Even the blue one is converging.
Will they
But
converge to the same point, or
it depends. So it depends. I mean, if they have found like the same point in your loss surface, it will be the same value. But if they are at different minima, you can say local minima, then the values might be different, right? So for example, this green one,
can I say
it's
that
saturating.
can I say that independent of the learning rate that we take for some finite epoch value, does all the learning curves converge
No,
to the
no,
zone?
no, that's not true.
Oh, okay.
That's not true. So even the green one, you can see that I don't think it's going to converge like at as good as this red one. And
Yeah.
again, the reason is like, okay, let me actually explain using this one, right? So if the green one is going to converge to this point, right? Then the loss value for this one is entirely different than the loss value at this point.
Yeah. Okay.
Okay. All right. So that was, I think there was another question from Sayed. How do we select good learning rate for training? Also, is it a good idea to change learning rate mid-training? And both are good questions. The first one is we do hit and trial. All right. You try to observe whether it's converging or not. And there is no ground rule like to figure out like what should be the learning rate. So that's the answer for the first question. The second one is it a good idea to change learning rate? And that's true. We do that. We keep changing the learning rate, and we not only change, we try actually different learning rates. So again, there are different algorithms to do that. It's an ongoing research, and usually you might want to try like different learning rates and then see like which one is working better. And the other thing is, as you are moving closer to your minimum point, then ideally you want to reduce your learning rate. So the reason is, initially you take bigger steps, but then as you reach here, you don't want to miss this point and then go here and then keep oscillating, right? And that's why as you train for few epochs, then you want to decrease the learning rate and then take maybe smaller steps. And the idea is like, initially you might be at a random location in your curve, right? But by taking some steps, you are actually moving closer to your minima, then reduce your learning rate. So that's usually that's effective. The other interesting thing which people have tried recently is cyclic learning rate. And what cyclic learning rate is, you start with a learning rate, you keep decreasing your learning rate, and after it's saturating, you again start with a very high learning rate. So again, that's a variation. I think we should not go into deeper, but again, as I said, there are a lot of variations in to that. So another question from Steven. Is it possible to set up dynamic momentum and learning rates? So learning rate we already covered, and of course, like momentum, yes, I'm sure there are some works which do that. Okay, so again, that's a good question. All right, so that's learning curve. Now let's move on to the problem of overfitting. All right, so overfitting is an issue which will happen a lot when you train your networks, and there are like certain scenarios which you will observe a lot. So one good scenario is if you have a very big network. So big network means you have a lot of parameters, and your data set is very simple. Then what will happen is, if you have too many parameters, you can easily memorize all of your training data, right? And I think there was a comment earlier, like using few samples is memorization. But if you use too many parameters, then you can actually memorize all the samples. So, and that's called overfitting. And we'll briefly talk about why overfitting is bad. Then the other extreme is underfitting, which means that you don't have enough parameters to actually learn the complex data. So your data set is too complex, but you don't have the capability, or network doesn't have the capability to learn that complex function. So in that case, that will be underfitting. And usually what is useful is, if you have more and more data, then there will be less chance that your network is overfitting, because you are seeing, you are getting more and more variation, right? Because of this diversity in your input samples. And that's the reason, like, you need lot of data to train your neural networks. Okay, so let's try to understand what is like a good practice to avoid overfitting and underfitting. One thing we can do is we can try to monitor the loss curves. All right. So in this one, a blue one is your training loss, and you can see that as you train further, it's the loss is going down. The green one is the validation set, and red one is the test set. So test set, we don't have to look into that because that's evaluation, right? But validation we can see, because as we discussed earlier, validation set can be used to fine tune your hyperparameters. So let's look at the blue and the green curve. You can see that as you are training your network, your loss for training is going down. Simultaneously, your loss for validation set is also going down. It's fluctuating, which is fine. But at this point of time, your loss for training is still going down, but your loss for validation is actually going up. So what does this mean? This means that your network is actually trying to overfit to your training data after this point onwards. And that is the reason it's not able to perform well on the validation set. And that's why the loss is going up. So we don't want that. And that's why what we can do is we can just stop training at this point of time. And this is like your best network. And then you can try this on your test set and you will get the best performance for these kind of loss curves. As compared to if you take like a model which is working very well on the training set, let's say this pointed, because the loss is lower. But when you will try that on your validation or testing set, the performance will be even worse. Okay, so that's like one strategy we use. The other strategy is we try to regularize the network. So let me question from Mert. Was this an example of overfitting? Slide 31. Yes. I mean, it could be overfitting, it could be something else as well, but yeah, overfitting because it's doing well on training set, right? And doing bad on validation set. So that's kind of overfitting. So the other strategy we can use is regularization. And regularization is something which is an attempt so that our network is not able to overfit on the training samples. And so the idea is allowing the network to use as many parameters as it can. So we don't have to compromise regarding like the size of the network or the amount of parameters we want to use, but still we don't want to overfit. And that's why we need a regularization. So let's first try to understand like why overfitting happens. Now let's look at these samples. So let's say these are your training samples. And in this case, I mean, it's not a complex problem, but again, the data is two-dimensional. So we just have X and Y. So if you quickly analyze this curve, it seems like a straight line, right? So if we try to learn a neural network or any function for this, it should be closer to a straight line. And then what will happen is if I give you some samples from testing, then again, it should be on that straight line and we should be able to make good prediction about that. So let's see what kind of functions we can learn using this data. Now, if we use like a lot of parameters, in this case, it's ninth order polynomial, right? So ninth order polynomial means you need those many parameters for that equation. And what's happening here is this ninth order polynomial, which you have learned, of course, using this data, this polynomial is going through each and every training point. And if you compute the loss on the training set, the loss is going to be perfectly zero. Because for each training sample, you have a perfect overlap, right? Because all the points are on this curve. So that's a very good training. Now let's look at another example, which is like just first order polynomial, because for a straight line, you just need like maybe two parameters like slope and intersection with the X or Y axis. So this is first order polynomial and it's a straight line. So in this case, what will happen is if you compute the loss of this function, then it will not be perfectly zero, because what will happen is if you look at this point, it's not completely overlapping with this curve. There is a distance between this point and the curve, right? So that distance will be accumulated as a loss. And again, if you look carefully at all the points, all points will lead to like smaller amount of loss value, but again, the loss will be not huge, but again, it will be not exactly zero. So this is the second fitting. Now, what will happen is, in this case, if I give you like a test sample, then that test sample will not fall on this polynomial. It will be very difficult. Let's say even if I have a point here, right, which seems like it's coming from the same distribution, so then the loss for the testing sample will be very high. So this is kind of an example of overfitting. And this you can say maybe not underfitting, I will say for this scenario, but kind of a perfect fit. All right. So this is kind of a perfect fit if we have this kind of distribution. So red is one class, blue is another class, and we can learn this polynomial here. And you can see that we are making some errors, like this blue is falling on the other side. Again, this blue is falling on the other side. Same for the red. But again, these could be like just outliers as well. And this is overfitting because we are trying to draw a very fine boundary between these two classes, right? So the loss is perfectly zero. And this is underfitting a straight line because you will get a very high loss value. So if you think about this curve is a straight line, means very less number of parameters, right? And this is kind of medium number of parameters, and this will require a lot of parameters. So that's why having high number of parameters leads to overfitting, and less number of parameters leads to underfitting. Now, as I said, like we use early stopping. That was, I think I explained by analyzing the loss curve. The second strategy is regularization. So what regularization does is we try to kind of control the values of the weights which we are learning. All right. And then we have dropout. I will explain these two in a bit. Just give me. Okay. And there are some other strategies. So early stopping we have already discussed. The second point was regularization. So what we do here is we try to penalize the parameters which we are learning if they have very high value. So the reason is, if a certain parameter will have a very high value, then it will kind of dominate the prediction of the network, right? Because essentially, like, you are actually doing linear combination inside your network, right? So given an input, if a parameter has a high value, again, there is a chance that it will give a very high activation, and at the end it will control what kind of output you are getting. So and that will lead to overfitting. So we to avoid that, what we do is we limit like how much what can be the amount of the value actually which are stored in these weights. And that's like one way of doing regularization. And I think there's a question from Stephanie. So overfitting occurs when we reach too many training points, and vice versa for underfitting. Yes, that's true. So you can say reach too many points, or you can say that you are kind of memorizing all the training points, right? And underfitting, like, you are not able to memorize anything or not even learn anything. Okay, so if you penalize like weights which have high value, so that will lower your overfitting. Now, this is an example of, as I showed you earlier, the blue one is overfitting, and the green is, you can say, perfect fit. So given a testing sample shown by like a triangle point here, you can see that if you use like the overfitting curve, then there is a huge gap between the curve and this point, right? So you're going to get a very high loss, which means that this blue is not a good curve. But as compared to green one, it's kind of making the right prediction. Okay, so then what we do is we try to control the weight values. So which will also, so if you have low weights, then the curve will be kind of smooth, right? You won't have these sharp corners, something like that. So not like one, it won't be like only one parameter is controlling the complete output curve. So then what we do is you have the standard loss function. So this first term is fine. Okay, you already know this thing. We add another regularization term. And again, we have a coefficient here which controls like how much regularization we want. So this regularization is on all the weights of the network. And what we can do is we can either use Elvin norm. So L1 norm is just like the value of the weights. We sum like all the weights in the network and try to minimize that. So which will ensure that we don't have weights with very high values. And we can have L2 norm. We can square the value and then minimize that. Okay, and we can have other variations like this is elastic net, which is fine. Another variation of trying to minimize the value of the weight. So this is kind of combination of L1 and L2 norm. So now I think it's a point. I think when we were talking about linear algebra, there was a question, I think from Sanjay or someone, who was asking like why we need to study L1 norm. So this is somewhere like a good application of L1 norm, okay, to do regularization in your network. I think there's a question from John. Does overfitting ever have application, or do we always want a smooth curve? Yeah, overfitting is never good because it's kind of, let me give you an analogy. So let's consider like a fifth grade student, right? And he was taught addition. So then he will have like, let's say 5 different examples where he will add values. Let's say 5 plus 7 equals to 12 or 10 plus 10 equals to 20. So what he can do is he can either learn how exactly addition works, and that will be like a proper learning, or we can say like a very good curve, because what will happen is then we can give or throw him any number and he will do the addition, right? The other thing is he can just memorize the samples, or we can say the training samples. Then he will be only able to add those particular pair of numbers. And then in the exam, if we show him different numbers, he's going to fail. So that's, I think, a very good analogy for overfitting and a perfect fitting, right? So a question from Russia. Overfitting is covering all the data points, then why is the loss function value not equal to 0 in overfitting? Yeah, overfitting means the examples I showed, the loss value will be perfectly 0. But usually it won't happen because you have a lot of samples, right? And all those samples are high dimensional. So it's not possible to actually memorize all of that. And of course, when if you train a very huge network, let's say trillion of parameters, then of course you will get a loss of 0, even with like those samples. Okay, so the second part is because we are eventually using all the data points except if the data point is an outlier. Actually using all the data points. Right, that's true. But I didn't get like what's the connection. So you're saying that, so I hope the first part is clear. And it seems like the second is connected. So Ruchia, so is it clear or you still have doubt? Okay, great. So, okay, so this is like a regularization, and the other way to regularize your network is to use a dropout. This is again very interesting. Now, what you do is you can actually use a lot of neurons in your layer, and in dropout, what you do is you randomly switch off some of the neurons during training. For example, if you have, let's say, 4 neurons in this layer, you can stochastically, let's say, turn off this neuron. Then what will happen is this neuron is not going to predict anything. And only these 3 neurons will be used. So that's like one iteration. And maybe in the next iteration, you do use this neuron, but switch off this neuron. So this will control that your network is, or each of the neuron is not actually trying to memorize your input data, because you are stochastically switching them on and off, right? So that actually helps in the learning and avoid your overfitting issue. Okay, so that's dropout. And so the other interesting point is we discussed earlier, right? You initialize the weights of your network randomly, and that's done because you don't want to initialize them like maybe like a same value, maybe 0 or something, because then what will happen is if all the neurons have, or all the weights have similar value, then the response is also going to be similar, right? Then you will not be able to train the network in that scenario. So in all the cases, I mean, you will always have to initialize it randomly. So that's fine. That's a, minor point, and of course there are different techniques to actually initialize a network, and some are said to be better than other, and of course one can argue that as well. Now, since we are initializing the network randomly, what that means is you have a loss curve, right? And when I'm saying that you initialize your network, then it's kind of you are picking one point in that loss curve randomly, right? And then depending upon what that initial point is, that will control what will be the output. Because it may happen that you have multiple minimas in your loss curve. Then for one initialization, you might go to like one minima point. For the other, you might go to a different point. So then this is useful, and what we can do is we can actually train multiple networks by different initializations, and later we can just combine all of them and create an ensemble. And I think again this was one of the questions I think in the previous lecture, and that's why ensemble is useful, because each network is giving you different prediction, and in a way like they are doing like good job on their own. So that's good. Yeah, we have covered dropout. So we stochastically turn off these neurons and make use of only few in one pass. Okay. So yeah, these two are another important points. I mean, if you do that, then two neurons will not like become friends of each other and try to learn something with the help of each other, right? So which means they are not going to co-adapt to each other, because sometimes one of the neuron might be switch off. Then this neuron will have to learn on its own. So it cannot rely on the other. So that's one interesting point. And this leads to like each neuron is useful by itself independently. It's not relying on any other neuron. And again, this is a hyperparameter. Usually we set like it to 0.5, and this hyperparameter is just saying that how many neurons you want to turn off at a time. So if it's 0.5, it says that 50% of the neuron will not be used. And of course, this is done only during training. When you test your network, you use all the neurons. Okay, so that's basically like all the steps or all the concepts we need to train your network. And let's briefly go over like what we need to be able to train a neural network. So first of all, we'll have to define a network. Once we have the network, we'll have to define a loss function. Then we randomly initialize the network parameters. Then we need some training data. And we'll have to prepare batches which will have to feed into the network. And for each batch, we will do a feed forward pass, okay, which means that whatever random weights you have, you just pass the input and do all those transformations and get the output. And based on that output, you will also have a ground truth. Then you can match those two, compute the loss. And once you have the loss value, you compute the gradients and then backpropagate those gradients to update the network parameters. So that will be like training of one batch. And then you repeat that for all the batches in your training data. That will be training of one epoch. I think there's a question from Sarat.
Yes, Professor, can you tell more about dropouts? Because what happens if two neurons in the same layer, I mean, two neurons in the same layer can't talk, right? So if the neuron in the next layer uses the neuron in the previous layer as its friend, then they will make a more conform, more decision. They'll make decision more efficiently, right? So why are you saying that since if the neuron is taking output from its friend, it will lead to some making, it will lead to making an erroneous decision?
So co-adapt means these two can like,
they can't talk, right?
No, they can't talk, but they can try to make prediction which will influence the output of the next neuron, right?
Yeah, they are able to influence the next layer.
Right. So it's not only about co-adaptation of these two, it's also about co-adaptation of neurons across the layers, right?
So can
So,
you more
for
define what
example,
co-adaptation means?
co-adaptation means they try to memorize something in your training data. So they rely on each other completely, which is not good. So this neuron should make a decision based on all these neurons. It should not just rely on this neuron. So what may happen is let me give you like a simple example. So essentially what we are doing for this particular neuron, we are learning all these weights, right, which are coming in from these neurons.
Yeah.
Right. So what can happen is that while training, this neuron can completely switch off all the other neurons and assign the weight of 0 and just try to infer based on whatever this neuron is outputting.
Okay.
And that's bad. But if you use dropout, so sometimes what will happen is this neuron will be switched off. Then this neuron will not be able to work, then you will get a very high loss value. Then it will, okay, try to adapt itself and then also try to learn from these neurons.
Okay. Are you saying that this node will try to learn equally from its below nodes?
Right. And that's what we want, right? That's why we have that many parameters. We want to utilize them, not just like just be there to like memorize something.
Yeah. Okay.
Okay. Question from George: why not just make a smaller neural network? That's a good point. And if you make a smaller network, then again, that may lead to underfitting, right? Then your network doesn't have a capability to learn complex functions. So there's a trade-off between these two. So more neurons are good because we do have a lot of neurons in our brain, right? But we don't do overfitting. We try to learn the pattern, not memorize. Of course, some may try to memorize as well, but then they will have to pay for that. Is it clear, George? Okay, but the neurons being dropped aren't being used anyways. No, they are being used. Okay, so when we are dropping the neurons, so we are stochastically dropping them in just one iteration. So for one mini batch. For the next mini batch, we drop like different set of neurons. Okay, all right, good. And that's what I said, like we drop during training and again stochastically, but during test time, we make use of all the neurons. So whatever they have learned, we will be making use of, from all of those. Okay, so then these are the training steps, and we discussed about LXNet, right? So these are the configurations which were used to train LXNet to perform pretty well on ImageNet. And by now, I think you should be able to understand every bit of like pieces which are shown in this slide, like all these numbers, what these layers mean, and what this network means, and all these hyperparameters. So the values or the kernels in your network, they are called parameters because they are learned. Then the configurations, these are called hyperparameters. So these are kind of settings which you use for training, but these are not learned. So these are like manually assigned by you. So that's why they are called hyperparameter, which are actually fine-tuned. You try to make use of validation set and maybe adjust these things. So ReLU was the activation function. Now you know what this means. A dropout of 0.5 was used. Again, you know what this means. Batch size of 128, SGD optimizer, movement of 0.9, learning rate of 1e minus 2. So the decay, I think one of you were asking whether we want to change learning rate. So we do that. And this is called learning rate decay. And this was done manually at that time, but today we have like sophisticated ways to do that. We can have adaptive learning rate. So what they did is they reduced the learning rate after the accuracy of the validation was saturating. And this decay was 5e negative 4. So this amount was decreased from the original learning rate. Okay, so these are all the parameters. So that's good. And I think, okay, there's a question from Tristan. So since we use batching, every neuron does get trained at some point during training since they are dropped at different times. Yes. So every neuron will be trained. It's just like they might be switched off for certain batches. But at the end, all of them will be trained. Question from Shivo. Are we going to have a coding session for CNN training in the future class? Yes. So today it's Thursday, right? Not during the class. So the coding session will be Thursday, Tuesday. So next Thursday during office hours, we will go through like whatever we have learned so far in CNN. And I think the next lecture where we will talk about how actually we code all of this. And then we'll have a live session. The TA will show you like how to actually train it. So that will be a good hands-on experience for you, and that will be useful for your programming assignment as well. And yes, Jacob, those office hours will be recorded. So I think we have a few minutes left. Let me quickly cover these couple of slides. Now, so this was AlexNet. So you can see that you have input image, you have these con layers, where you have kernels, you try to extract features, and then you keep learning like complex features from those activations, and at the end you make prediction. So let's talk about like a few variants of these convolutional neural networks. The first one is residual networks, and the idea behind residual networks is that, so let's say this is your input, and again this could be your image or this could be your activation map, and this is your weight layer, which means that it could be your CNN layer, then again an activation, then again let's say a CNN. So these are trying to learn features from this. These weights are trying to learn features from the output of this one. Then what we do is we simply add like the features which were learned before this layer at this point of time. And there are like a lot of reasoning why we need to do that. I will give you like one very important reason why this is very useful. So the first reason is the features which you are learning at this stage, they might also be useful at this stage. So that's like one intuition. And if you try to represent that using functions, it will just like fx plus x, right? X is the original input, and fx is like this output of this two layer function here. And this is also called kind of a skip connection. You are using features extracted at higher level and sending them to like a layer at a lower level. So why this is useful? So we have studied that you have a loss function, you find the gradient, and then you backpropagate that gradient to the initial layers, right? Now what happens is if your loss is very small and if you compute a gradient, then eventually that gradient might be very small as you go like to the previous layers, and mostly like if you have a very deep network, right? So that issue is called vanishing gradients. So then what is going to happen is if the value of the gradient is too small for the initial layers, then essentially you're not updating those bits. All right, so that's one thing. So then if you have this kind of skip connection, it actually helps you train deeper networks. And the reason is, let's say you are at this point of time, so you will have some gradients, right? Now you will compute gradients for this layer, and then for this layer through this path, but you will also backflow your gradients through this path because this is an addition operation, right? And you know that for addition, you distribute your gradients. So whatever gradients you have at this point of time, they will flow back directly to here. So even if your gradients are vanishing from these two layers, whatever gradient you had, it's going to get back here. So the issue of vanishing gradients will be resolved. And if you have that, then even if you have very deeper networks, you won't face this issue because in each like of this skip connection, you are actually sending back the gradients directly without going through these layers. All right. So this allows you to train deeper networks, as I said, helps in backpropagation. And based on this residual architecture, we have a lot of CNNs these days. The first one was a ResNet architecture. And again, based on ResNet, we have a lot of variations, but this is the basic idea behind all of those. Question from Abhishek. So skipping one layer act as a regularization effect so that we train for more deeper networks. Yes, that's true. Because if you don't have skip connections, then you will face the issue of vanishing gradients, right? But if you have these skip connections, then you will be able to backpropagate easily. Now, the second type of network, it's inception. And the idea here is, first of all, you want to lower the memory consumption, not memory consumption, you want to lower the number of parameters which are required. The other interesting idea here is in each layer, you want to learn or extract features at a different resolution or different scale. So what you do is you use convolution like very small filters, just 1 cross 1. So it's just doing a transformation on that pixel value. And you can also learn 3 cross 3. You can learn 5 cross 5. And again, you can have this 1 cross 1 after max pooling for like translation invariance. So even like it's just one layer, but you have all these variations. So this helps you in learning better features at different scales. Okay, so ResNet, which we discussed earlier, was about going deeper, training like deeper networks. Inception is like you have a wider network, because in single layer you have like these variation of kernels. All right, then another variant we have, this is called DenseNet. I think there's a question from Curtis. Is this the same as a recurrent neural network? Curtis, no. So recurrent neural network is entirely different. We are going to talk about those as well later in the lecture, but this is not recurrent neural network. Question from Mert. So this is the layer version of Dropout. I don't think you can make that analogy because this is not Dropout, right? You still have both the connections, and so I'm not sure, like, no, you're not even regularizing here. It's just mean you're adding that skip connection, which is helping you in a better back propagation. Okay, so the third variant, and I think we will end after this, is DenseNet. So this is similar to ResNet. The only difference is instead of sending the features to the next layer, you send the features to all the future layers. So for example, if these are the conf features after the first layer, you send it to the next one, and you also send it to the layer after that, and a layer after that, and a layer after that. And in ResNet, we were just adding these features. In this case, we are concatenating these features. All right. So that's why it's called ResNet, DenseNet, because these skip connections are very dense. And then we can have these dense blocks, and we can just stack them on top of each other. And this is like the architecture for DenseNet. Okay, so yeah, that's all I think I have. We are already over time. Let me see if we have any last minute questions. Okay, so that's good, Matt. You understood. So any last minute question before we end? All right, if not, that's good. Of course, feel free to send me an email if you have any question. So let's end it here. Thank you. Bye.